Hi there, my name is Jacopo Masi from USC ISI, and today I'll be talking about our paper, Two-Branch Recurrent Network for Isolating Deepfakes in Videos. Take the two videos in front of you. At first sight, they both seem authentic, genuine videos with real actors. Nevertheless, after we run our face manipulation detector, we can see that the right video presents more traces of face manipulation than the previous. Indeed, the video on the left is the original pristine video, while the video on the right has been realistically generated by manipulating the pristine video to swap Steve Buscemi's face over Jennifer Lawrence's face. The video on the right is a deepfake, and in this work we are interested in detecting this family of face manipulations. The contribution of our work are as follows. We propose using a two-branch recurrent network to work in both the color space and the frequency domain. The network is supervised by a new loss formulation for isolating manipulated face sequences. As a minor contribution, besides accuracy, we employ global metrics at low false alarm rate. Finally, our system reaches a good trade-off between bias and variance when evaluated on three datasets. Our system takes as input aligned face sequences to assess their likelihood of being manipulated. As you have seen in the introduction, it can also localize a video where the manipulation may be. These sequences are pre-processed by two branches. A branch processing the signal in the color domain, and another branch using a Laplacian of Gaussian filter to remove the low-frequency components of the face and to propagate other frequencies. The two branches are fused using one-by-one convolution with two different groups, so that each group is specialized for each branch. The backbone of the network is based on three dense net blocks and uses dropout to avoid overfitting. The temporal dimension is reduced using a bidirectional LSTM, which is supervised through a new loss formulation. Inspired by prior work, the upstream part of the method is composed by a two-branch structure that propagates two different signals to the backbone. One branch propagates the original information in the color domain, while the other branch suppresses the low frequency of the face content, yet amplifies multi-band frequencies using a Laplacian of Gaussian filter as a bottleneck layer. In this way, the backbone received a different set of feature maps. The downstream part of the network ends with a bidirectional LSTM to reduce the temporal dimension of a sequence. We found best performance by concatenating the two bidirectional outputs. The recurrent network and its convolutional part are supervised through a new loss formulation for isolating manipulated sequences. So let's review how this formulation works. We begin by defining a reference center C by pre-computing the LSTM embeddings of the real face sequences only. We then define an hypersphere to bound the natural face sequences. The phase sequences inside this sphere will not incur any loss. The radius of the sphere represents the margin of the natural points. Natural points outside of the sphere will incur a loss that will pull them towards the center, thereby applying an attractive force. We also have a larger hypersphere for manipulated sequences defined through another radius. Manipulated sequences outside of this margin will not induce changing to the model weights, while manipulated points that are in all the other region will be pushed outside of this latter sphere. You can see that the two hyperspheres induce a margin between which is defined by the difference between the two radii. We can now see what happens to the geometry of the feature space using t-SNE. You can see how the natural faces are compressed inside the inner sphere, while manipulated faces lies all around. The same property transferred decently well on the test set. It's finally interesting to observe the cluster formed by each video in the feature space. As I mentioned before, the two hyperspheres define a margin between the classes that greatly improves performance. If we take a look at the regular logic distribution, you can see that the main clusters of the natural and manipulated faces are far apart. Yet the variance of those distributions is not minimized. And if we zoom into a high confusion region, the logic are mixing each others. Instead, if we take a look at our distribution, we have induced compactness of the natural faces and pushed the manipulated faces far apart for a better separation between the two distributions. This induced improved results at low false positive rate. We now describe a few takeaways useful for deepfake detection. When training on multiple face manipulation, it's imperative to have a balanced ratio of manipulated sequences and natural sequences in the mini-batch. On Face Forensic++, the ratio between natural versus manipulated faces is 1:4. For this reason, we undersample each manipulation twice, and we oversample the natural faces twice. In this way, the mini-batch is balanced on average. We also found very useful for cross-dataset testing to do early stopping, or else to decay the learning rate quickly. Also very important, given that the videos are redundant, it's useful to use stratified sampling and define an epoch as going over a random sequence for all the videos in the training set. Our approach obtains promising results on Face Forensic++, which is the dataset used for training, when testing the four manipulations: face swap, face-to-face, deepfakes, and neural texture. Besides looking at the low false alarm rate, we can just show accuracy. It should be noted here that a classifier exploiting the class imbalance can get an accuracy of 80% by simply predicting all the sample as fake. In our case, for classification, we use the middle sphere between the two margins and obtain superior performance than the state-of-the-art. We also obtain good performance when looking at other metrics at low false positive rate, both for the medium quality C23 and low quality C40 when compared to ExceptionNet and DSPFWA. When cross-testing on CelebDF, we use the model trained on all four manipulations and optimize with the data with the low compression level C40, and we report a good transferability to CelebDF compared to prior work, both at the frame level and at the video level. Note here that although the AUC passes the 70%, the values at low FAR are still not very satisfactory to be used at large scale on the web. Finally, we also tested our method on the Facebook DFDC preview set, showing performance that greatly improves the precision while achieving a high recall of 90%. To conclude, we have proposed a deepfake detection method that was optimized for reaching a good trade-off between bias and variance across datasets. That is, our approach performs very well on the dataset used for training Face Forensic++, yet it's transferring very well on other datasets such as CelebDF and DFDC. Thank you for your attention.